For today, we are going to look on propeller theory. So the propeller theory will be divided into two lectures, lecture number 7 as well as lecture number 8. So we are going to go through halfway for today, probably most likely until the topic of aerodynamics design before we continue on lecture 8 on this Thursday. It's a replacement class, our third replacement class, to look into the remaining subtopics. To begin with, about aircraft propellers, we are going to look into the introduction before we continue on some nomenclature. It's good to be familiar with the terms being used in the propeller theory. With regard to aircraft propellers, we know that aircraft propellers or air screw convert rotary motion from piston engines or normally turboprops to provide propulsive force. This is going to be shown in a later figure in the next slides, figure 4.24, and they may be of fixed or variable pitch. Before we go any further, probably you are wondering why chapter number 5, but our numbering here is 4.4.1. So the reason why is that in the book that we are referring to, okay, it is a continuation of piston engine and propeller engine. So it is a combination. In the textbook, the propeller topic is parked in chapter 4 together with piston engine. That's why it is the numbering. I would like to continue so that we are not going to be confused in terms of the numbering. All right. So in both cases, about whether the propeller is fixed or having a variable pitch, the propeller normally accelerates a large quantity of air through a small velocity change. So this is the advantage of having a propeller set of propulsion system. In a turboprop engine, normally 80% to 90% of the thrust is produced by a turbine-driven propeller, and 10 to 20% it is produced by the jet. Okay, most of the propulsive force are being driven by moving a large quantity of air through a small velocity change. While in piston engine, propeller produce 100% of the thrust force. So it is being shown clearly in this schematic, a propeller that being installed in a piston engine, right? This is a piston engine. You can see the velocity that incoming into the propeller that is installed in front of the piston engine, and the large arrow indicated more air going into the turboprop engine. This is a schematic of a turboprop engine. So the for piston engine, the arrow being indicated by small arrow here, but for a propeller turboprop engine, we have a larger mass of air being moved by changing small velocity, velocity change that also produce the jet velocity. Okay, we are going to talk more on this in our topic today. Before we go any further, propeller has several definitions as being highlighted here. A device having a central revolving hub with radiating blades. You can have more than 2 blades. It's not necessarily only 2 blades for propelling a vehicle. A vehicle can be an airplane, can be ship, or anything else, right? So as long as it is a device that having a central revolving hub, it is called a propeller system. Okay, it is also be defined as a device which consists of a set of two or more twisted airfoil-shaped blades mounted around a shaft and spun to provide propulsion of a vehicle through air or water. Of course, it's not through space because there's no medium over there. And propeller also can be defined as a type of fan that can transmit power by converting rotational motion. It requires rotational motion either from piston engine or turboprop into thrust to pull or to push the airplane. So the propeller itself can be situated in front of the engine. So we call it as a pull type of propulsive system, or it can be placed behind the engine that denoted as the push. It can be a push to the airplane. Okay, it can also be defined as a series of rotating wings or airfoil of equal length meeting at a center hub which is attached to the crankshaft of aircraft engine. Right, let us look into some glossaries or nomenclature. Okay, and in order to explain the theory and construction of propellers, it is necessary first to define the parts of various types of propellers and give the nomenclature associated with propellers. So probably all of you have already seen a propeller, but we want to really define what are the components of a propeller. What is it called? What is this middle part called? What is this part being named, and so on. Right. In these particular figures, it shows a fixed pitch. So the pitch is fixed. It cannot be twisted. Okay, on one piece of wood propeller. So propeller can be made by many type of materials, and in this particular example, we have a wood propeller which is designed for light aircraft. So you can see some critical components. This is before we go into that. So you can see here, this is a propeller having a twisted blades. You can see the blades are being twisted, and there are also cases there are straight propellers. It's only it's not being twisted like this particular example. So in the middle there, we have the hub. It's a round shaped parts at the hub, and in the central of the hub, we have a hole. We have what we call it as the hub bore, which is connected to the engine itself, and over circumferential of the hub bore, we have the bolt holes, right? And this part is called the blade shank, and this is the twisted blade in this particular case, and the blade tip. We also have some propellers having a metal tipping. Later on, we are going to see examples of propellers that are having metal tipping. In this particular case, we do not have, because it is a wooden type of propeller. Okay, just a more detailed definition of a hub. It is basically an integral component located on the exterior of the vehicle or the airship or the aircraft that is connected to the propeller blade. So basically, the hub in the example that being shown earlier, it is integrated. It is one piece, and the wood is being carved in such way to have only one component. Okay, it is one piece, and then we have the shank, the thick rounded portion of the propeller blade near the hub, which is designed to give strength to the blade, right? And then the blade tip, of course, the maximum reach of the blade from the center of the hub. Okay. So more schematic being given here. The cross section of a propeller blade is typical of a typical airfoil section is shown in figure 4 to 6, a cross section of a propeller. So you can see here it shows two views and various cross section of a propeller blade. So bear in mind that the propeller itself is not only having one type of airfoil shape, and it has many type of airfoil shape which we are going to look into later, right? So over here, basically, in this particular case, it is not like the wooden propeller. Wooden propeller is one piece. In this particular example, it has a connection, which is connected through the hub center line, where the same we have looked here on the black blade shank in the wooden propeller just now. So this is the back of the blade, okay, and the shape of the airfoil, okay, when it is being twisted, it is thick near to the hub, okay, and it's become thinner. The cross section, this particular figure, the black shaded area here, is basically you are looking at the cross section for the blade itself. So it is thicker near the hub and becoming thinner when it reached the blade tip, right? Of course, at the same time, the blade also having blade angle. This is a plane of rotation, okay, where the blade face is basically down here, the blade back is on top of this. So we will look into more detailed explanation later on with regards to the blade angle. With regard to the blade shank, which has already been defined earlier, is the portion of the blade which is near the butt of the blade. It is usually thick, right, to give it strength, and it is cylindrical where it fits the hub barrel. But the cylindrical portion of the shank contributes little or normally nothing to thrust. So it's just to secure the blade to the hub. So in an attempt to obtain more thrust, some propeller blades are designed so that the airfoil section or airfoil shape is carried all the way along the blade from the tip to the hub. So it is carefully being designed in such a way the angle of or the airfoil section shape, and the one that we have seen here, it is carefully being calculated and being designed so that it can maximize the thrust produced. Right. In other designs, the airfoil shape is carried to the hub by means of blade cuffs. Blade cuffs, which are thin sheet of metal or other material which function like cowling, right? So the cuff is hard rubber. So this is the cuff. So the rubbery, like on the black area here, is the hard rubber shape that changes the airfoil of the propeller to more advantageous shape near the spinner. So this is the spinner, okay? So we have the blade over there. We have the cuff. This particular cuff can be shaped easily compared to the metal kind of blades, okay? Single propeller with cuffs. Right. Let us move into the classifications. So with regard to classifications, we are going to look into the following subtopic. We are going to touch upon first on the source of power, then material, coupling to the output shaft, control, number of propellers coupled to each engine, direction of rotation, propulsion method, and number of blades. You can see that in our topic lecture today, lecture 7, we are going to introduce the basic fundamental knowledge about propeller theory. Later on Thursday, in lecture number 8, we are going to go through several examples with regards to thrust, produce, how to calculate thrust, how to calculate efficiency, and so on. So for today, it's just a very light lecture to look into the terminology and the examples in terms of what are the nomenclature being used. All right. So with regard to classification in this particular section, the classification for propellers based on different points are being identified. It is important to state here that classification listed here are applied for both the piston engine as well as the turboprop engine. Okay, so classification will be followed here after based on different items that I have already listed in the content just now. So let us look into the source of power. Okay, right. As seen in this particular figure, figure 2.4 that we have already seen in our earlier slide, it may be either driven by a piston engine, okay, crankshaft of a piston engine, or by a turboprop, which is connected by a turbine shaft of a turboprop engine. Okay. And materials, we have seen materials such as wooden propeller. It is a solid, or sometimes wooden propeller also being made by laminated wood in very early types, which were used exclusively on personal small aircraft or business aircraft prior to World War II. And that's why we rarely seen a modern aircraft using propeller anymore. Okay, using wooden propeller anymore. Okay, and we used to have metal type of propellers, or we can also have layer. The later types of metal, and after 1940s, propellers were made of steel, but recent propellers are fabricated from high strength, which is normally been heat treated aluminum alloy, different type of metal. And metal propeller is similar to the wood propeller, except that the sections are generally thinner. Okay, there are advantages and disadvantages of having either wood or metal. And then more modern type of aircraft, modern design using composite materials since 1960s. Glass and fiber polymer composite propeller materials were used for manufacturing propellers, right? More, and if you look into more modern type of aircraft, okay, they are already use 100% composite materials. Today, nearly all the large propellers for aircraft have carbon fiber blades, like Lockheed Hercules C-130J or the A400M made by Airbus, also using composite materials. So these are lightweight compared to wood as well as metal. Composite are lightweight, which have high specific strength, normally has a stiffness, high stiffness, and excellent fatigue resistant, and its resistance to erosion are 3 times that of aluminium alloys. So that's why no more wood or metal type of propellers being used in modern aircraft design for piston as well as the turboprop engine. Okay, 4.5.3, coupling to the output shaft, right? So direct coupling, where you can see that through a reduction unit, you have the propeller being connected directly to the engine, where you have a reduction gearbox in the middle before you reach to the piston engine. Okay, so this type of engine, they have a reduction gearbox, and there are also type of piston engine that is connected directly, and this is the old type of piston engine. Okay, they have a direct coupling. Okay, and then some being used a reduction gearbox, right? To have more control on the propeller rotation, right? And then talking about control, 4.5.4, we have fixed pitch normally being used for small aircraft. Blades are fixed at a certain fixed angle to the hub, where the blades are cannot be turned. It is fixed. They are having fixed angle and usually never change. It can only be altered on the ground only and not during flight. So this is a limitation for fixed pitch type of propeller. And we can see here the Wright brothers developed the first successful propellers of the fixed pitch type. Okay. And then, of course, we have the variable pitch, the opposite of the fixed pitch. We have the variable pitch, which is normally bigger and more sophisticated planes. Blades may be rotated about its long axis. It may be subdivided into two types. One is two-position propeller, where the blades are limited to two angles. Okay, it can be changed into one type of angle, maybe 30 degree, and the other one probably 45 degree. Or other type of angle. One normally being used for takeoff and climb for low speed operation, and the other for cruising. You want to have high speed operation. The other one of type of variable pitch is adjustable pitch. Once whose pitch can be altered by the pilot. So during the flight, the pilot has the liberty to adjust the pitch of the propeller. Okay, this is called the controllable pitch, which has automatic mechanism to adjust its own pitch to match the plane's flying speed, right? So different angle of the blades can produce different thrust, right? And then the other one is the constant speed type of propeller, which is designed to change pitch automatically, allowing the engine always to turn over the same constant speed, right? That's why we call it a constant speed type of propeller. Right, the next one is feathered type of control for propeller, which is turning the propeller blades so that they are edge on, making a very shallow angle to the oncoming air, minimizing air resistance, right? So, and allowing the plane either to keep on flying on its remaining engine or glide to a crash engine, right? So this is a control with regard to feathered. On a single engine aircraft, the effect is to increase the gliding distance. Sometimes when the engine does not working, the propeller itself can still turn. This is what we call the feathered control. On a multi-engine aircraft, feathering the propeller on a failed engine allows the aircraft to maintain altitude. Okay, so it can be used to probably restart the engine, or the pilot can decide what need to be done, and with the reduced power from the remaining engine if you have multiple engine aircraft. Then in terms of the control of thrust reversal, the pitch of the blades can also be reversed, right? So a propeller makes a forward draft of air instead of one moving backward, handing for extra braking. And normally you want to make sure that this type of aircraft, normally turboprop aircraft, they can be producing reverse thrust. And when they land on a short runway, okay, the pilot can engage thrust reversal so that the pitch of the blades can be reversed, so that the propeller make a forward draft instead of a backward thrust. Okay. This particular table 4.7, which illustrates a comparison between fixed and variable pitch propeller. from performance and cost point of view. All right, so you can see here a basic function of poor performance. Let's say fixed pitch propeller. Okay, it is poor performance. It has a basic function if you have a fixed pitch propeller, but you have a lowest cost. Very easy to install and very easy to maintain, but you are having poor performance. If you have a constant speed propeller, it is the best performance, but most expensive to be constructed, right? And then, of course, in between, you can have a ground adjustable propeller or in-flight adjustable propeller. So the moment you have more complicated components, right? So of course, the engine is going to become more heavier, right? You want to have all the mechanism to adjust the propeller pitch, and it becomes more complicated and more expensive. But it is in the other way is that it will produce the best performance, right? So you have to decide whether you want to have better performance or better cost saving, right? Okay, let us look into the number of propellers coupled to each engine. So how many propellers can be coupled to each engine? So you can either have a single type of propeller coupled to an engine like what we have shown earlier. Okay, and then you can also have double type of propeller, contra rotating. You can have a three-bladed propeller in front of here, and you can have another one at the back here. And this is a contra-rotating propellers on Rolls-Royce Griffon, powered P-51 unlimited racer. This type of aircraft, P-51, being used in World War II, when the Americans having war with the Germans. They are using P-51. This is the type of engine, Rolls-Royce from the UK, but the aircraft is being used by the Americans to fight the Germans. And then contra-rotating propellers, also referred to as coaxial contra-rotating propellers or high-speed propellers. It apply the maximum power of an engine or more engines to drive two propellers in contra-rotation. And rotation about the same axis in opposite direction. That's what we call a contra-rotating propeller. One is rotated in one direction, the other one is in the other direction. These two propellers are arranged one behind the other, and power is transferred from the engine via a planetary gear. It has of course to have a complicated gear connection or spur gear transmission. Okay, direction of rotation. Let us look into direction of rotation. And for wing installation of aircraft, you can have either even number of engine. You cannot have one engine installed in the wing. So normally it is balanced side by side. You can have either 2, 4, or 6 type number of engine. So propellers may be having same rotation direction. So all engine, if it is 2, both engine having same rotation direction for both wings. The propellers on both engines of most conventional twin engine aircraft spin clockwise as viewed from the pilot seat. Clockwise from the pilot seat and not from the people on the ground. Okay. And then we can also have propellers having counter-rotating arrangement. Right wing has clockwise propeller rotation. Left wing has clockwise propeller rotation, or vice versa. It depends on the arrangement, right? The advantage of such design is that counter-rotating propellers balance the effect of torque and the P factor, eliminating the problem of the critical engine. Okay. counter-rotating pairs on each wing. So a good example is Airbus A400M Atlas. So the military cargo aircraft by Airbus. Okay, the pair of propellers on each wing of the A400M being shown in the next figure for 430 turn in opposite direction with the tips of the propellers advancing from above towards the midpoint between the two engines. And this is in contrast to the overwhelming majority of multi-engine propeller-driven aircraft, where all propellers on the same wing turn in the same direction, but not for Airbus A400M. Okay, like what being shown here, a typical A400M. So on the if we look on the aircraft, this is the left hand side for the aircraft, but for the pilot view, it is a right wing having engine 1, 2, engine 1, engine 2, engine 3, engine 4, and engine 1 and engine 3 are having different rotation. And you can see one is clockwise, the other one is anti-clockwise, and vice versa over here. Okay, it is having a different rotation. Okay, propulsion method. We want to move to 4.5.7, right? Propulsion method can be, for propeller type of aircraft, can be pusher, where the propeller blades are being installed behind of the engine. Okay, like this kind of Piaggio P180 Avante. Right, sorry. The left picture showing Piaggio P180 and the AUV on the right. This is the by the US Air Force. So you can see that this type of propeller installation, we call it as a pusher. It is not a puller. So it push the aircraft forward, and similarly here it push the UAV forward, right? And then we have the normal type of propeller installation, which is the puller. We call it tractor. So the rotation of the blades will pull the aircraft forward instead of pushing the aircraft forward. Okay, the puller propeller installed to Antonov AN140-100 aircraft, like being shown in this particular figure. Or you can also have a combination of a tractor and a pusher. Okay, a puller or a pusher type mounted in line on a small aircraft. Okay, you have two engines. One is installed in front, where we have the tractor or the puller type of propeller, and then this is the pusher type of propeller behind the aircraft. Okay, this is a Cessna 337 Skymaster. Right, number of blades. Okay, one has the option of setting the number of blades for a given application depending on your choice, while one has a minimum of 2 blades to choose from. One can presently go as high as around 8 blades on the high performance end for an unducted propeller. You can have 2, 3, 4, 6, 8 type number of blades. Okay, so what we have here, the multiple number of blades greater than 4, as an example, 8-bladed Hamilton Sundstrand NP2000 engine, which is installed on the C-130 aircraft. Okay, so you have 8-bladed number of blades propeller installed on the C-130 aircraft. Okay, so I believe it's best to stop here, right? So that we can have a short break before we move into the next subtopic, the aerodynamic design.